So this time we have one of the easiest series tests that we're going to have so far. This is section 11.5, which is the alternating series test. Now in the last video, I ended with a series which I couldn't apply any of the tests to because it wasn't a decreasing positive term series. Because so far all of our tests have required either we already have a geometric series, a telescoping series, or we have a series with strictly positive terms that's decreasing. So we have a test from when that doesn't happen, but it's still a little bit strict. So an alternating series is a series which simply has alternating positive or negative terms. You're positive, then negative, then positive, then negative, etc. So the alternating harmonic series is -1 to the power of n divided by n, and here we use -1 to the n to denote the alternating behavior, because this is equal to -1 plus +1 over 2 plus -1 over 3 plus 1 over 4 plus a -1 over 5, etc. So the test is as follows. If the alternating series, written as the sum from n equals 1 to infinity of -1 to the n times b sub n, satisfies b sub n greater than 0, basically I have positive terms that are multiplied by -1 to the n, which represents the alternating signs, positive, negative, positive, negative. B sub n plus 1 should be less than, well, or equal to b sub n, meaning the b sub n's as a sequence should be a decreasing sequence. And the limit as n goes to infinity of the b sub n's should be equal to 0, which is kind of a mandatory requirement for the convergence of any series. Then the alternating series must converge. Now again, this is a test that doesn't tell me where it converges, it just tells me whether or not it does converge. So using the alternating harmonic series we had already, I can rewrite this as n equals 1 to infinity, -1 to the n times 1 over n, so this is my b sub n. 1 over n is positive. 1 over n plus 1 is less than 1 over n. That's always true, so this is a decreasing sequence. And the limit, as n goes to infinity, of 1 over n is definitely equal to 0. So unlike the regular harmonic series, the alternating harmonic series must converge. Now I think this one in particular, since I'm starting with -1, should converge to negative natural log of 2, if I recall correctly. But sometimes the alternating nature can be hidden a bit by the representation of the series. Take, for example, the sum from n equals 1 to infinity of n cosine of n pi divided by n root n minus the natural log of n. Actually, since I have a natural log of n here on the bottom, I should start... No, it's okay. I won't be dividing by 0 if I plug in 1. I was a little worried. Now, believe it or not, this is actually an alternating series. And the reason for that is if we try to list out a couple of terms, we're going to find out that every time we try to evaluate cosine, we're either going to get +1 or -1. In particular, we have cosine of 1 times pi, this cosine of pi, which is -1. Cosine of 2 pi is +1. Cosine of 3 pi cycles around the circle once and lands at pi, which is -1 again, etc. So I could rewrite this series as n equals 1 to infinity of n cosine of n pi, no, rewrite it, come on, as -1 to the n, because I started at when n equals equal to 1, I got -1, and when I was even, I got +1, times n over n root n minus natural log of n. So this right here would be my b sub n. But the problem I have is I need to know whether or not this is decreasing and whether or not the limit goes to 0 as n goes to infinity, because these are my two conditions. We'll do the easier one first, which is the limit as n goes to infinity of the terms, which is n over n root n minus natural log of n. And this is kind of similar to infinity over infinity, but strictly speaking, I should change to a continuous variable instead of a discrete variable, whatever that means. So I'll rewrite this in terms of the real variable x. As x goes to infinity, x root x minus natural log of x. And this goes all the way back to 11.1. And now we can use L'Hopital's on this. We'll end up with 1 over x root x, x to the 3/2 power. So I should have 3/2 x to the 1/2 minus 1 over x. But as this goes to infinity, I end up getting 1 over infinity, which is basically 0. So that checks out. Now what I need to do is make sure that these b sub n's are decreasing. And that looks really hard to do by comparing general terms, so what I'm going to do is switch it over to x's. I switch it over to a function of the real numbers. So b sub n becomes f of x equal to x over x root x minus natural log of x. Now something that's true, if I take the derivative of this function and find out that the derivative is consistently negative, well, that means my terms in my sequence are likewise going to be decreasing. Because if I have a constantly negative slope, then my x values are consistently decreasing, and therefore the sequence terms will be decreasing. So I'll find f prime of x, which that requires a quotient rule. For the top first, I'll have 1 times x root x minus ln of x minus x times the derivative of this here. I've kind of done this above, so this would be 3/2 root x minus 1 over x. And this is all divided by the square of the bottom. Now let's see if we can't clean that up a little bit. I have x root x minus ln of x minus 3/2 x root x plus 1. That should be squared. So I have similar terms here and here. So I have -1/2 x root x minus ln of x. Looks good for being negative everywhere. Oh, but I have a plus 1. That shouldn't ruin too many things, because as n goes, or as x goes to infinity, that plus 1 probably won't matter anymore. So it looks like as long as, let's say, x is greater than 2, or equal to 2, f prime of x is definitely negative. Because as x values get larger than 2, they'll become larger and larger, versus the 1 stays the same. So I'll have a 1 minus eventually a very big number. And that's exactly what I need, which means, so if my function is consistently decreasing, then my associated sequence, b sub n, must be decreasing as well. So I've satisfied both terms, or both conditions of my alternating series test, which means that my series must converge to something. But what we'd like to know is what it converges to. And unfortunately, we can't know that. But we do have an estimate. And this is based on how the alternating series works. So an alternating series basically works like a bunch of floating bars. So I'll go up somewhere, then I'll subtract some off, but it's less than the first amount. I'm going to add some back, less than the first amount. Because my alternating series, when I add alternating positive and negative terms, I'll add and subtract and add and subtract. But every time I cancel something off from the previous operation, it's less. And so I eventually kind of narrow in on some limit, which means that the remainder, or the error, of the alternating series is always less than the next term. So the alternating series remainder, if the sum negative 1 to the n of b sub n, so my alternating series, if it converges, then the remainder r sub m of estimation by a partial sum s sub m is always b sub m plus 1, the next term. Wherever I stop adding my partial sum, the next term is my remainder. Well, it's the upper bound for my remainder, I should say. So if I wanted to find out what the remainder of adding up the terms of the harmonic series up to 5,000 terms, then I would just literally look at the 5,001st term. It's actually that easy. So not to oversimplify this test, sometimes the steps to verify the conditions of the test can require an extra amount of work, but that's really all you need to do for each of these tests. Once you've verified that you have an alternating series, so you have a negative 1 to the n multiplied by some positive terms, then you just got to make sure that it's decreasing and that the limit of those things goes to 0, and you're all set. And whenever you want the error bound for estimation, it's always the next term right after you stop. Or if you're looking for the smallest integer n, for which you need to reach a certain amount of precision, then you just need to stop previously to wherever you found your error bound.